Okay, so this is super introductory, and it's meant to be super introductory, so it will be low level. But those of you who this is new should find it interesting because it is an interesting topic. First I'll just talk a little bit about classical encryption techniques and security techniques, and then point out some of the issues we have. I do come from the cybersecurity side of the world, so I can talk a little bit about some of the issues we have, but I'll keep it all high level, partly on purpose, partly because that's really my understanding of this material at this point. But then we'll get into some of the, I'll bring up some of the physics that, quantum physics that are relevant in this discussion, and go over some quantum cryptography ideas, but really spend the most time probably on the quantum key distribution techniques, the two schemes that there are. And I'm just going to really, I don't think I'll have much time at all to really get into too much quantum networking itself, but I will mention it and leave that for another day at depth, as I need to learn a little bit more about it to be comfortable enough to describe it to people. But then, we'll talk about what's going on with the post-quantum cryptography world. And then in this document, which I'll share, I'll store and put into the archives, for the meetups with the annotations. You can look at it later. I have a whole bunch of references that might be of value to you. And again, the microphones are on for you to turn on and off as you choose, and feel free to pipe in anytime you've got something to say. I welcome that. So, essentially, the thing is, data security and encryption. Oh, I got my pen. There we go. Data security and encryption is all over our lives today. It's ubiquitous. And when it comes to security and encryption, really think about data in two ways at this level. One is data in transit and data at rest. So you could think of, data at rest is where, you're storing data on a disk or in some file somewhere. And that's data at rest. Data in transit is where you're essentially transferring data across the internet. Now, if you really want to get into it, data in transit also includes CPU to things like RAM inside your machine, which, from a cybersecurity perspective, is actually a pretty exposed area that is starting to be addressed by encryption being implemented even at the data bus level. So anyway, so when you exchange emails, we do chat, the Zoom right now is encrypted, etc. That all is based on basically a secret key cryptography technique. And that is where, if I've got data here, I encrypt it using a secret key, I transmit it. You also have access to the same secret key. And so when you receive the data, you can unlock the encryption and see what's called the plain text. So that key is essentially a key string, and essentially it's something that looks like this. Either when it's in transit, it's kind of encryption technique that essentially encrypts each bit as it gets transferred. And if it's an encryption method at rest, it's a key that kind of just goes through all of the data and encrypts it and stores it in the encrypted format. So the process going from plain text to ciphertext is called encryption, and to go from ciphertext, the encoded text, to back to plain text, the same plain text, is called decryption. So important to note that in this particular case, anyone can see this ciphertext. If you're sitting at Starbucks or what have you, it's very easy to capture the Wi-Fi ciphertext floating around in the air. You could also, if you tap into the wires in the under the ocean, on the ocean floor, you could also grab that ciphertext as well. And in fact, some three-letter agencies do capture that ciphertext now and store it, even though they don't necessarily have the capability to decrypt it yet. But we're okay with people having the ciphertext, because without a key, the person with that ciphertext will not be able to make any sense out of that message. And this is the most important point for anybody new to the notion of electronic cryptography, that believe it or not, it's as simple as all this encryption is basically just based on a very difficult math problem, one that all the supercomputers in the world put together could not solve. Not because the problem itself is very difficult, but because of the way that the problem itself is put together. You can't really solve the problem in any mathematical or systematic way. It really boils down to some guesswork, if you will. So if you tried to brute force a solution to this math problem, it would take you forever. And this math problem and there are different techniques, mind you, but the one that's most widely used is based on prime factorization. And essentially what the math problem is, I have a very large number, 1, 4, 6, 7, blah, 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 let's say 300 digits long. And I take that number and I need to figure out the two factors that when multiplied together equal that very large number. So, hold on. There we go. And I'll show you an example of that in a few minutes. But those two factors are, the trick here is they're two prime numbers. So you just can't say, let's say there's a number 456 and you wanted to find a prime number there. 2 is a prime number, and so that would be 2, 8. The ability to figure out these two prime numbers is oftentimes left to guesswork. Now there are some techniques to reduce the amount of guesswork necessary in figuring out the two prime numbers, but still the computers are not able to do it in any reasonable amount of time. So basically factoring is considered a one-way function. So it's very easy to multiply two numbers. 3 times 7 equals 21. It's very easy to multiply them and check that the two numbers are correct, but it's very difficult to take the number 21 and figure out what the two prime factors are, which happen to be 3 and 7, by the way. And it's easy for us because most of us, at least my age, have memorized the 12 by 12 multiplication tables, and so we can easily factor the number 21. So it's based on a difficult math problem that's really, it's considered a one-way function. It's easy to do one way, but very difficult to reverse. And this is essentially known as the TLS encryption technique. And so if I had a number, let's say something in the area of 2 to the 256 power, which is basically a 1 with 300 zeros behind it, it would take approximately 12 million years on a supercomputer to solve. Hold on a second. Stop the video too. There we go. All right, so now the encryption, the keys are are these numbers here, the 3 and the 7, the two factors. Now, one of the fundamental problems we have, if let's say the keys are 3 and 7, is how do we go about exchanging these keys? So for A and B to exchange data, they need to both know the key. And so this key exchange problem is like a separate science, if you will, when it comes to encryption and computer security. So these keys, these pairs of numbers, somehow need to be exchanged in advance. And that's what the RSA protocol is used. It's a widely used standard for the exchange of the two private keys. And RSA uses what's called a public key to help facilitate the exchange of these two keys. I'm not going to go into a lot of detail of it, but essentially think of it as something like the number 21 is actually public in this equation here. All right, so if I have if I'm one person and I have the number 3 and the public key is 21, then I know the key for my counterpart, B, is 7. And if I'm B and my key is 7, I know the key is 7, and the public key for you is 21, then I know the other side of the equation is 3. So I'm greatly simplifying this, but there's more to it than what I'm describing. But in short, you could think of it as a triage of a public key and private keys. So, you know, that's how RSA essentially works, roughly. So if I have the public key, again, 21, you could, and I had one number 7, I could easily figure out the other number 3. And if I had the public key at 21 and I have the number 3, I could easily figure out the number 7. Not exactly the way it works, but it's close enough for our purposes here. And actually, there was a good exercise somebody did the other day in some presentation somewhere along the line that I thought was quite good. So let's try something here. So if I gave you the number 15, could you factor that into two prime numbers? I would argue, yes, you could easily and quickly figure out it's 3 and 5. What if I gave you the number 49? You could also quickly do 7 and 7. Actually, that won't work because they're duplicates. Let me get my calculator out here, and I'm going to figure out a quick one for you. Let's say, what's a prime number? So if I gave you the number 115, how long would it take you to figure out what the prime number for that is? Okay, go ahead and try it. Ultimately, what you should get is 23 and 5. Anyway, I gotta figure out a better way of showing this little test here. The point is, as these larger numbers get larger and larger, A, you can't do it in your head anymore. B, it takes you a long time to essentially, you have to go through and brute force the answer to this question. So you'll see very quickly the amount of time it takes to factor two numbers looks something like this. It's an exponentially difficult problem. So when you get up to a number with 300 zeros in it, you're basically in billions of years. But again, the key here is that creating the number 23 times 5 is very quick and easy to do, but to go the other way takes quite a while. And for our encryption today, it's essentially, we believe anyway, it's impossible. So what are some of the issues with security, in particular data in transit? You really have two main things to think about. One is the notion of eavesdropping, where if A is here, B is here, there's a somebody out there, a computer or a person, sitting there, and there's data in transit sitting in between both of you, where that C is eavesdropping. So they're basically copying the data that you're sending back and forth. That's one thing that we're all fearful of. And, you know, RSA encryption, TLS encryption, etc., have helped deal with this, at least in the near term. And that's the thing we have to be careful of, because that's one of the drivers for this quantum computing craze right now, is that while eavesdropping is easy, the decryption of that data is hard. But as we all are becoming aware, a quantum computer using Shor's algorithm will make the decryption of this stored data very, very easy to decipher. Another problem with the current state of affairs is what's called a man-in-the-middle attack, and you'll see it as MITM quite often, so sometimes they don't even say man in the middle, but if you see that in security documents, that's what they're talking about. And what it is if you have A and B here, there's a computer, usually owned by a person, that can position themselves in between you. And the problem here is, if the data is not encrypted, the attacker could, you could have hello here, the attacker gets your hello, and instead of just passing on hello, as in the case of the eavesdropper, the attacker instead changes the message to blue. And vice versa, messages coming from B get changed from X, and the attacker, if he or she chooses, can send Y to the victim, to this computer here. So the victim, or the A here, is getting a completely different message from B, and so that's the equivalent of sending emails under somebody else's name. You just could imagine the damage that would do. Or if this computer here wants to transfer money to B, what the attacker could do, they could take the foreign exchange information, for example, make a change to it, and send it off to the banking system, and either not pass the message on to the original bank, or pass the message on to the original bank, perhaps slightly changed, etc., and no one knows that anything has occurred here, to either change the message or intercept the message, etc. So now that's known as a man-in-the-middle attack, and those things are particularly nasty. It's the equivalent of someone going in and changing the emails between you and the receiver, or between the sender and you. So if that eavesdropper has the key, they can see all, and you would not even know it. So these attacks could be completely transparent to you. As many people refer to in the quantum cryptography world, this is the big problem of the day. Messages being sent globally, internally within governments, everything else, all these messages, although they're secure at the moment, later when quantum computers become widely available and Shor's algorithm becomes something in practice, all of those secrets can be decrypted. So things like, the JFK assassination was in the 60s. It takes around 50 or 60 years for a lot of that information to be released. I believe some of it, for example, is not even released today because some of the principals are actually still alive. So that's one example of where, we, for whatever reason, we want data to be secure 60. And, I could imagine in some of the political realms between countries, you'd want information to be stored or kept secret for even 100 years, as crazy as that might sound. So again, quantum computers can figure that out pretty quickly. But no worries. Presently, those quantum computers are not large enough to cause any problem. In fact, I believe the largest number so far, and obviously the largest number to be factorized by a quantum computer, is around 144 or something like that. I mean, it's a pretty small number. Obviously, that's 12 times 12, but that's not, so that's 3, 4, 3, 3, 2, 2. Anyway, I think, if I remember off the top of my head, the largest number to be factorized by Shor's algorithm, I think, is something like 144. Not 144 digits, but the number 144. All right, so let's get to the fun stuff. So, any comments before? This is a good stopping point. Any comments, issues? Okay. All right. So, first of all, when it comes to quantum physics, oh, wait a minute, I think there were some chats. Were there some chats out there? 91 is 13 times 7. Yeah, okay. Yeah, agreed, George. All right, so, first of all, when it comes to quantum physics, the physical laws of the very small are immensely different than the physical laws of our everyday experience. And this is known as quantum mechanics versus Newtonian physics, or quantum physics versus Newtonian physics. Newtonian physics are the physical laws that we see in our everyday experience. But at the atomic and subatomic level, this quantum physics kick in, and I don't quite know the difference between the terms quantum physics and quantum mechanics, but for my purposes, they're essentially the same thing. It's the physics or the mechanics of the very small. And one little tidbit for new folks in particular, quantum the word quantum itself does not mean small, which is what I used to think in the very early days, but it actually means quantized, which means discrete chunks. So that's a little trivia question. I'm sure physicists are totally aware of that, but as newbies, that was news to me, frankly. All right, so here are some concepts from quantum physics that have a part in quantum key distribution and quantum internet. First of all, an important thing to keep in mind is the notion of decoherence. So this is where the particles are affected by their environment, and therefore they can change very quickly. And if they change quickly, they actually lose their information. And so, you know, it's not like random access memory or in a classical computer or memory on a disk. Those things do not decohere. You put a 1 in a certain spot on a disk, it will stay there, and it will not just kind of fade away over time as things do in quantum mechanics. So, you know, you can't just, you know, take some data A, B, C and put it away somewhere and let it sit for a day or two and then use it later on. So we have this notion of decoherence to deal with. A key point is the Heisenberg uncertainty principle, and this will come into play in one of the techniques I'll show you in a couple minutes. And that this uncertainty principle is that you cannot know all the information about a quantum particle. In other words, you can only measure a portion of the information while the other remains unknown. You know, in I think they call it the wave duality, I think, in protons. If you've seen a double slit experiment, is it a wave or is it a particle? Isaac Newton and those guys argued about that question back in the 1920s. But, you know, associated with that is, you know, you can't know all information about a quantum particle. I can't explain it. I don't think anybody can, but that's just the law of quantum mechanics. We also have the notion of a no cloning theorem, which means you cannot, it's impossible, note the word impossible, to create an identical copy of a particle's state. All right, so the no cloning theorem really makes programming a quantum computer enjoyable, but it also makes the notion of a quantum internet quite difficult to implement because, you know, frankly, when in the classical networks right now, if I send data from my computer to yours through the internet, it actually gets copied. The actual bit that I am sending, the bit of information, is not physically the same bit on the other side. What happens is that bit gets copied countless number of times as it goes from essentially, you know, my storage device to your storage device. Well, we cannot do that in quantum mechanics. Another important feature that I'll try to show an application for in a few minutes is the notion of entanglement, and that is you can, if I had two particles, I can entangle them so that their states, the states of the two particles, are not independent of one another, aka they are correlated in some way. And then superposition, so that is where each quantum state can be represented as a sum of two or more other distinct states, and that's where you see the ket notation you know, when we're programming a quantum computer. And we also have the measurement problem, which is basically, I consider that an opportunity in quantum computing, but it's essentially where whenever you measure a particle, you will find the particle in a definite state and not a superposition state. So we can easily put a particle in superposition, but when we measure it, it loses all the characteristics of that superposition state and essentially ends up being what we recognize as an information bit of 1 or a 0. All right, so let's get into the quantum piece, cryptography. So when it comes to the notion of a quantum internet, the very first step is really deal with this quantum cryptography, which again, cryptography we use for data in motion or data at rest. So here, this is the big takeaway. So in quantum cryptography, instead of depending on the math, which we believe Shor's algorithm is one way to break the math, the secrecy now depends on features of quantum physics. So, based on what we know now, if we really use these quantum physics, there's really no way known to man so far to break quantum physics, to clone, for example, a particle. So this is a much stronger way of, if we can rely on quantum physics over just a very hard math problem, we basically eliminate the threat of a powerful quantum computer. So if you recall the Heisenberg uncertainty principle that I mentioned a few minutes ago, where you cannot know all the information about a particle, you can only measure a portion of it while the other remains unknown. So notice that we can measure part of the information on the particle, but the other remains unknown, and that's actually a helpful thing in this case. So if you imagine an encryption key, where before it was a number, those keys are essentially streams of photons, aka light particles, instead of a series of zeros and ones. And in our classical computers, it's usually, plus or minus 3 volts, or, some fluctuation in electrical voltage. So these photons are quanta. Remember, that's small pieces of electromagnetic field, and are traveling in waves that are both electronic field and magnetic field waves. So they're waves. And I'm going to avoid any questions by physicists at this point. I welcome comments by physicists, but not questions, please. So a light wave, for example, has a wave that kind of is think of it as maybe a horizontal wave, but it also has a vertical wave as well. So that's an interesting feature that we'll take advantage of when it comes to key distribution in cryptography. So the light wave, or protons rather, have really 2 schemes. One of them is known as the rectilinear scheme, and the other is known as the diagonal scheme. So, one of those is the wave going this way, and the other is the wave going that way. So in one case, the rectilinear scheme, think of it as the wave going vertical and horizontal, and the diagonal scheme, think of it as actually left and right diagonals. So you could think of it as going like that, or you could think of it as the wave going like that. There's 2 schemes. One scheme is this way, and the other scheme is this way. This is rectilinear, where it's either going north or east, and here it's at an angle, let's just randomly say 45 degrees pointing to the left, or 45 degrees going to the right. So you can measure the polarization by going through, by having light go through a polarizing filter which is essentially what your sunglasses are. So think of it as light going through in these two different schemes. And if I had a filter here, notice that it's up and down. So only the up and down light will come through. The light going in the other scheme will not get through that. Notice that, see the blue does not get through. And this is essentially roughly how your sunglasses work. And so when you refer to the rectilinear polarization, think we use this symbol here, the cross, and the direction essentially goes north and south, and it could go east or west. But in the diagonal, we'll use this symbol here, where the direction will go at an angle like this, pointing what I call to the left, or be going in this direction, pointing to the right. Now, in this case, so here we'll use a 0 if we're measuring in the rectilinear mode. We'll refer to 0 when it's going up and down. We'll just say that represents a 0, and if it goes horizontal here, we'll say that represents a 1. And here, if the orientation on the diagonal is pointing to the right, we'll consider that 0, and going to the left, we'll consider that 1. So there's a really cool experiment that I can't do online, but you can, I'll try to get you to appreciate here. So here, if I have some light coming in and I have a rectilinear filter, it will allow just this orientation light to come through. Okay, so it's blocking all of the east and west light coming through because I have a rectilinear filter here. Now, forget this for a minute. If that light were to continue through and I had another filter, another rectilinear filter, and I had it oriented to east-west, then what would come out? What would you expect? So if I had one filter here, filtering north-south, light comes in. The only light that comes out is this direction. And then I had another filter that measured, or that was a filter in the east-west direction. What do you think the light would look like when it would come out? Well, there would be no light because these are up and down, and this is a left and right filter, and so therefore none of the light can come out. Now what's really freaky, and it's really cool to do this in person, I have the filters. I bought some filters for a few bucks to try this at home, and that's what really gives you that aha moment. The interesting thing is I could put another filter in here. If I put in one of the diagonal filters, the diagonal filter in here, which is what this is representing, what will happen is I'll actually get light coming out. So instead of having two rectilinear filters blocking the light, if I put a diagonal filter in between those two filters, right, what happens is I actually get light coming out again rather than it being blocked. It's kind of spooky. So imagine I had two pairs of sunglasses or two filters, and I put them on top of each other. I have no light coming out. But if I take that third filter oriented in a different way, then notice I'm getting light coming out. The third filter is in between the original two. Here's filter A, here's filter B. A is, let's say, filtering that light, B is filtering that light, therefore I get nothing. Here is A filtering this light, here is B filtering this way, and if I put in C here, filtering at an angle, it actually allows, this is in between A and B, it actually allows light to come through. And that's essentially what this is illustrating here. It's really cool to actually do this. I just hit my mouse and I just lost everything here. Flashback. All right, so let's get into how do we use this. Blah, 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 man in the middle attack. So is one where somebody intercepts it and actually changes the information, or at least can. So the first thing is, let's take a look at quantum key distribution. Here's where it might suddenly become interesting. So quantum key distribution is nothing more. Remember I said we need to get the key in the proper keys into the hands of A and B. And so all we're talking about is sharing. How do we share those keys between the two counterparties? It does not, by the way, solve the authentication problem. So if I'm not really B, if I'm an imposter B, B2, and I'm pretending to be them, this is not going to solve that issue. That's called authentication issues. But it essentially makes undetected eavesdropping impossible. And notice, I'm not saying eavesdropping is impossible, but undetected, it would be impossible with this scheme. So there's two basic schemes. The first one is based on the Heisenberg uncertainty principle, and that is where you cannot simultaneously know the values of certain pairs of properties. And by the way, they're called conjugate variables. So I don't know yet the relationship between the conjugate when it comes to a complex number and a conjugate variable, but I'll figure that out eventually. But I'm sure there's overlap in what the word conjugate actually means. So for example, you cannot know the position and the momentum of an electron. You know either one or the other. And the same thing with the polarization orientation of a photon. So the photon polarization is either rectilinear, recall, or diagonal. And they are complementary properties. So if you measure one properly, you lose all the information about the other. And any particle that is unmeasured is considered in superposition in both rectilinear and diagonal states. The act of sending a proton through the polarizing filter forces the proton to make a choice. And that choice is first which basis it is in, then which orientation it is. So which basis being rectilinear or diagonal, and then once the basis, and you've heard this term basis in quantum computing quite a bit, and here's partly what we're talking about, then which orientation it is. So it's either up and down or left and right, or if it's diagonal, it's either pointing to the left or pointing to the right. And this Heisenberg principle is the basis for what I believe is actually the first quantum key distribution protocol invented or discovered, and it's known as BB84, which some of you may have heard of before. And that's that's named after the authors, Bennett and Brassard, and the year was 1984. So if you think about the rectilinear, 0 is rectilinear like this, 0 is vertical, and I'm sorry, horizontal, and vertical is 1, and in the diagonal pointing to the right is 0, and pointing to the left is 1. So keep that in mind. So I took the liberty to use some graphics from a video. So until I can actually create my own, I'm not a graphics guy. So for version 0.1 of my stuff, I'm going to borrow instead of create, but I'll get there eventually. So imagine you have A and B, and this is, by the way, this is BB84 I'm describing here. And I've heard many people say BB84, etc. And so this is what you want to understand. So A essentially selects some data. And remember, what we're trying to do here is we're producing a key and then sharing that with the counterpart. So we'll create some random bits, and then we'll then randomly select the basis for those bits. So notice here it's got the two different bases, but I randomly select some bits, then I randomly select one of the bases in which to measure or in which to orient the bits in the string. So then what I do, so here I've got, the bits, and then here the orientation is rectilinear, here it's diagonal, rectilinear, etc. And then this is the corresponding value. So horizontal for rectilinear is 0, pointing to the left for diagonal is 1, etc. So I basically transform these bits through a random basis, and I get these results. So these photons then are then sent to the counterparty, B. So now B has those measured or those oriented photons, okay, just like you do over here. B then randomly selects, because B doesn't know the orientation or the basis of these photons, so B randomly selects some bases in which to measure these photons. And therefore, when B measures those photons using the randomly selected basis, aka the polarizing filters, B will come out, will then decode the protons according to the basis that B selected. So think about those polarizing filters or those sunglasses at work here. So B then deciphers or transforms the decoded protons into bit values. So here, because B measured in a diagonal basis, and notice the proton came in at a rectilinear basis, B gets pointing to the right here, which corresponds to the value 1. Here, the protons coming in, and B does not know this yet. B does not have this information. B has the proton, but doesn't know what these directions are, what these measurements are, because B has not. So B doesn't see this, but B uses these filters and sees this. And so when you see and B uses a diagonal here, sees the light, the proton in this direction, therefore it's a 1. Uses a diagonal, sees it in this direction, therefore it's a 1. Uses the, I'm sorry, the diagonal, gets the, I think this is an error here. Yeah, that should be pointing in one direction or the other, because the light's coming in and we're measuring on the diagonal, it should, diagonal basis, it should be pointing to the left or right. I have to check that out later. Here, we're measuring in a rectilinear, so I'll get a rectilinear result, that's a 0, and so on. All right, does everybody follow this process here? This is really, well, the gist of it. Any questions, anybody?
I have a question. So are you using rectilinear or diagonal for each separate bit, or are you choosing one or the other for all the bits?
It's for each separate bit, which is that's a good question, it's an important point. Each bit is, so here's the light coming over to B, proton, right? Yeah. And so the first bit, the first proton, B is going to measure using the diagonal basis. Randomly selects it. And the second proton will be measured randomly in the diagonal, third randomly in the diagonal, fourth randomly in the rectilinear, randomly in the diagonal. So yeah, each bit is essentially paired randomly with one of the bases. Very important that this is random, but yeah, each bit is separate. So if the proton is coming in having been essentially filtered by A with a rectilinear, right? So this is light. So A is sending the proton over having been filtered with a rectilinear filter, so it's coming in either left and right or up and down. And then this filter here is randomly selected, not knowing anything about this proton here, is randomly selected as a diagonal. So B is going to get a diagonal measurement. So here, for example, let me see. So here, B randomly had selected a rectilinear basis for this particular proton coming in, number 1, 2, 3, 4, and therefore, of course, gets the filter allows only rectilinear light through, and in this case, it's left and right, which is the value of 0. So yeah, absolutely. Every bit is paired with a random choice of the filter being rectilinear or diagonal. And so what B gets then is a bunch of bits that look like this. So next, what happens is B then sends the orientation list, or the basis choices that B used, sends those bases, the list, over to B. And so so here, basis, this list is sent over to B, and B sends this list over, and they're compared. So when the bases are the same, so here this is diagonal, this is, I'm sorry, rectilinear, this is diagonal, and so they ignore that first bit. In this case, it's diagonal and diagonal, and so they know that this bit here is to be kept. So they match their bases, and they realize, okay, the first basis, we didn't do it. We did not have the same bases, so we're going to ignore the answer. The third bit, this was a rectilinear, and B used a diagonal, so that's ignored. And so we'll ignore this guy. And then here, both of them randomly chose a rectilinear, so we'll keep the value that they have, that each of them have. See where we're going with this. So ultimately, when they pair up the bases, the choice of basis, they now have matching values. So 1, 0, 1, 0. See that? 1, 0, 1, 0. So without sharing, all they've shared, all that's transpired is they've identified the share bases. And from knowing that they have the same bases, they can keep the measurements that they took and know that the counterpart has the same values they haven't sent the values between themselves. They've only sent the bases between themselves. So that essentially becomes a shared key. Now, if going to man in the middle, if the man in the middle got these beams of light or these protons of light, and just as B does, randomly selects some bases in which to filter this light through, the man in the middle will have these values here. I'd have to check that one error to see if that's still persistent. But so this light, the light now that gets to be as we see here, is run through the process by B, where B selects the random bases or filters in which to process the light. B gets this bit string based on his or her measurements. Okay, and then this is the basis that B used. So B and A compare their bases, and so then this one here, 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 all become matched bases. But if you take a look at the values that the two counterparties, the two legitimate counterparties have, which is 10001 and 10110. A thinks the key is this, B thinks the key is this, and clearly when they send a message back and forth, because the keys don't match, they won't be able to read the message, or in particular B would not be able to read the message. Therefore, B knows that there was a man-in-the-middle attack. If there was not a man-in-the-middle attack, everything would have been hunky-dory. If that's a phrase anymore, I'm not sure. But everything would have checked out. So the key that A used and the key that B used, they'd be, exchanging messages and living happily ever after. But now we would know when there's a man in the middle in the mix, which is impossible to know in our present world regime, because you can copy data, etc. So this is essentially BB84. Think about it. I'll have the images available to you later, but it takes a few times, and even now I'm still not entirely comfortable with it yet, but I'm starting to get it. Essentially, we're sending light, filtered light from A to B. B. So there's light going through. B runs it through a filter of a certain basis. A filters it. B then puts another filter to the light and gets a measurement. The waves, let's say, going this way. And they then compare the filters they used and discard the light or the values that they got when the filters are different. They only keep the data that is the same when they use the same filters. I'm sorry, they only keep the data that is from the instance of where they had the same filters. And they get a key. 1101, 1101. Now, if they get something, if they go through this process and B thinks the key is this and A thinks the key is this, they'll find that they're not unable to decrypt the data. Therefore, they know that somebody inserted a filter in the middle here and changed the orientation of the proton. Just like, I go back up to the top here. Just in the same way, and this is really a rush to do in person. If you've got 3 sunglasses, you might be able to do it. I would assume the sunglasses have to be exactly the same type. But essentially, this is a man-in-the-middle attack. And notice how the results are different. Here, light's coming through, and here there's no light. If there was no man in the middle, you would expect no light to come through, essentially. But if somebody stuck a filter in between, some light would come through, and you say, hey man, there's somebody's done something between here. So, you know, B&B thought of this in 1984. You got to give them some credit for creative thinking, I must say, because I doubt I would have thought of this in 100 years. Any questions, thoughts, comments, please? Are you there? Is there anybody out there? There's got to be something. Wait a minute, there's some chat blinking there.
I'll toss
Yeah.
out a question. And how does A and B actually compare their values and their keys? Do they do that over a conventional line or over the telephone? Or
I must say, you know, that's the irony of the whole thing. Yes, they use classical techniques to exchange this information. Yeah. So every talk I've seen so far, you know, here's the quantum stuff, but there's this classical channel out here where you do all the quantum magic, but still they're communicating over a classical channel. So, you know, all the scenarios I've seen so far, and correct me if I'm wrong if somebody knows differently, but all the quantum key distribution techniques so far include a classical connection. So we're not getting rid of classical computing. But, you know, this is huge. The fact that you can know that there's a man in the middle. Right now, without this process here, you don't know if you're being hacked, essentially. With this process, you do know. And this you know, it's out of my range to describe much further, but this is the setup for, imagine I give my social security number to the bank. I mean, this technique I think can apply to, I give the social security number to the bank encrypted, and using the Heisenberg uncertainty principle, if someone happens to read that data or try to read that data like a man in the middle, I will know that, because when I decrypt the data, it'll be different. It'll be 1284 instead of 1234. So I've known someone's looked at that data, which right now, you know, if I give my social security number to Facebook, they can copy it, 1234, or even if it's encrypted, whatever, they can copy it and send it wherever, they can clone it and send it wherever they want. And I would never know that. There's no way I could tell. But here, I think this is the setup for a significant, a possible technique for privacy protection. Because this BB84 provides evidence that someone has looked at my data besides A and B. If you think about that. Anybody got any comments or have thought about it in that way? Oh my gosh, it's 8:20. Jeez. Give it some thought. I mean, this is a conclusion I'm starting to come to, is actually, you know, BB84, this notion here, using quantum physics, the laws of quantum physics can be applied towards things like, you know, privacy protection. Now, I can't prevent somebody from doing it, but at least I know somebody read it. You know, let's say a password, for example. I would know somebody has seen my password, so I can change it. Social Security number is probably a bad example because I can't change it. But a password, I would know. I have to think about it. Maybe that'd be something, homework assignment for somebody out there. Think about this scenario in password handling, which is essentially what this is, come to think of it. So, all right. I'm just going to quickly go through the second scheme. Obviously, I've rambled on too long again, but let me just create some awareness here. The second scheme that is, the basic scheme of quantum key distribution is known as Eckert 91, and it's essentially similar to BB84, but it also takes the advantage of Bell's inequality, which I'm not really comfortable with. Anybody out there have a good 15-second, 30-second explanation of Bell's inequality? Well, let me go through the technique then quickly, and then we'll end here in a few minutes. So essentially, A creates some entangled pairs. Okay, so that means that these electrons are correlated. So each pair is correlated with one another. A sends over the second of each pair over to B. And then A chooses a series of bases in which to measure the particles. So filters, or bases more particularly, because when they're talking about spins, where this is electron spins. So we'll basically get these measurements, right? I've got an electron here. I choose this basis here, so, oh well, my Amazon Lady A just talked to me for some reason and said, hello, we're very happy you're here. So anyway, so if I have a particle electron with a spin and I measure it using this basis, I'm going to get this measurement. And this basis using this, I'll get this measurement, this basis, this measurement, and that basis, this measurement. And keep in mind, the paired entangled electron is over here in B. All right, so I get the up, down, left, right, left, right. And so that choice of basis, by the way, represents a set of bases of bits here. Then B randomly chooses some bases in which to measure the entangled pairs. But because A measured the one half of the pair, these suddenly, or whatever the proper term for it is, because this side of the pair is measured, this side of the pair now takes a particular orientation. And B doesn't know this in orientation yet and measures the orientation and gets these results here. Because B's using this orientation. Now, they compare the results, and because here they used the same basis, but got different results. Notice here's, oh, I'm sorry, that's good. This one's a spin down, they'll be opposite. So because they use the same basis, they can trust the results here. Here they use two different bases, so they just ignore these. Here they use the same basis, see, the horizontal basis, so they keep that result. And here they use two different bases, so they ignore that result. Now, if someone had tampered with them, they would have, just like they had in the BB84, they would find that they'd have different results. So quickly, you know, that's the that's using entanglement in Eckert 91 to distribute a quantum key in a manner that if there was a man-in-the-middle attack, that then the results when A and B compare, or when they use the key, it would not work, and because a man in the middle had affected that process. So I'm just skipping over here quickly, but you know, essentially, you know, if the man in the middle measures it, then B will get different results. So I have here, and you could take a look at it later, I found a nice chart that kind of summarizes what we walked through in a more compact way. I encourage you to take a look at this and study it for a few minutes, if not a half hour, and you'll start to see what's going on here. But it's essentially a much more condensed and compacted version of what we walked through a second ago. So as I said, you know, this technique, although I haven't heard professionals talk about it yet, other than one person mentioning it, made me think about it, but it actually, these techniques could actually be used for privacy. And in the quantum networking space, you want to take a look at a technique called Bennett 93, which is, it's very similar to the approaches of the prior two, but you know, it's how quantum information is being transferred through, you know, in the form of a network. And then finally, just as a FYI, there is encryption. There are encryption techniques being developed, and they're referred to as post-quantum cryptography. So these techniques, which are being catalyzed by NIST, which is the National Institute of Standards and Technology in the United States. They're having not really a competition per se, but it is a competition of sorts where people are proposing entirely new methods aside from using the math factorization problem, still using math that that will not be possible, possibly broken by a quantum computer, at least believed not to be broken by a quantum computer. NIST has a process. They're in round 2 now, which I think, don't quote me, but I think there's something like maybe 23 techniques right now, round 2 techniques. I think there were originally 81. They narrowed it down to 23. They're evaluating, the public is evaluating those 23 techniques, and they're hoping by 2023, probably add a year now because of the recent stuff, that they'll have a post-quantum cryptographic technique that will therefore not be beatable by a quantum computer. The people that work in this space, I talked to a few of them, and what they expect, it's just like a quantum computer device where we don't expect one best answer. What they believe, there'll be actually a few techniques coming from this NIST process that, you know, each one has a strength and a weakness. No one technique will be dominant. They think that they won't find a completely dominant technique like we did with RSA, for example, or the factorization problem, which is pretty much a dominant technique, although that's being replaced with other techniques in cryptography. But anyway, the point is that, you know, there is work being put forth that, you know, may say to the quantum people that, well, we don't need your quantum computer for distributing keys, etc. So anyway, you know, I mentioned there's a few, a pile of references here for you to take a look at. What's useful, and I chose not to use in this, but I may reconsider that after the experience of watching Matt and his work. But there are some simulators out there that might be a better vehicle than using snapshots when learning about QKD. So anyway, I'm starting to lose my voice, and it is 8:30, and I've had your attention much longer than I expected. So that is it for any prepared remarks. Any questions, comments that anybody has, like to share some ideas? The microphones are open for you sports fans. I left you speechless, confused. Hopefully this is something to think about. Yeah, somebody? All right, well, oh man, I'm beat. I'll end it here then. I encourage you, you know, I think this, like a lot of things quantum, my sense is, and I'm starting to find this is a lot easier than it looks on the surface. It just takes several rounds to dig into it and try to understand it, myself included. Frankly, I'm not comfortable with what I'm describing here yet. It's not second nature, but I'm gradually getting to the point where I'm starting to see it. So, you know, I encourage each of you to take some time to try to understand this. It's really not that difficult. I think it's just a little confusing at the start. All right, so I hope that was of use, and I think we'll stop it here. Last call for questions.